Okay, in this presentation we're going to look at a Poisson random variable. So this is used in an insurance situation. The number of claims which arise under an insurance policy of a particular type in a year is modeled as a Poisson random variable with parameter lambda. Okay, there we go. A random sample of 600 such policies gives rise to a total of 72 claims in 2019. Okay, so determine the approximate probability value of this result in a test of these hypotheses. Okay, now essentially what we're doing here, it sort of suggests a hypothesis test in the first instance, but what we're really asked for is a probability value. Okay, so essentially what we're going to be doing down here is an approximation of some sort. Now, particularly what we're interested in is this value here, for the alternative hypothesis. Well, it's actually this 0.14. That's what we're particularly interested in. Under the null hypothesis and the alternative hypothesis, this is the hypothesized mean for one mean rate parameter or rate lambda for one policy. Now, this is an important thing actually. Sorry, just what I have on the screen here right now is correction factors. Okay, so it's a fair, right? There's a couple of different scenarios, and each scenario has its own way of dealing with the correction factor. Now, I'll just sort of draw your attention to two we're going to be using here. So essentially knowing what to do. Okay, so just one of those two there. Actually, I'll just draw your attention to those two in particular. Okay, it's a bit of a judgment call what we're going to do in here. I'll pick one, but really you can sort of pick the other. Just explain what you're doing. Okay, so this is the discrete distribution here, and this would be what you would do when you model it as a normal random variable. You just add or subtract 0.5. Okay, now it takes a while to remember all of those, remember what to do in each situation, so there's a good bit of work in that. Okay, that's actually that's the key outcome of this video, really, just sort of highlighting all the uses of the correction factor table. Okay, now the rate parameter here, lambda, is a mean expected. It's the rate parameter for one policy. So for 600 policies, we're specifying 600 lambda as the rate parameter. Okay, so the total number of claims, x, is a Poisson random variable with parameterized with 600 times lambda. Okay, so just as a remark, we note that the expected value and the variance of x are also going to be 600 lambda, and that we have a pretty large sample size. Essentially what I'm doing here with this part is I'm just sort of setting out the justification for using the normal approximation. Okay, which is something you should do. Don't just sort of state it. I'm being a little bit brief here with my presentation, but just actually make the case for using the normal approximation. So under the null hypothesis, with lambda equals 0.14, under the null hypothesis, x is a Poisson random variable with lambda equals 84. And if we approximate that with the normal distribution, the mean is also going to be 84 and the variance is also going to be 84. Okay, so that's the normal approximation there. Okay, I just edited a bit out, so I'm back on track. So we're asked to calculate the probability value under the null hypothesis that the mean is 84 and the variance is 84. Okay, so essentially we observe 72, okay, out of 600. So 72 from 600. Okay, now specifically what we're interested in is the 72. And what is the probability of x being less than or equal to 72? Okay, now I'm going to hear less than or equal to. Okay, but equally it sort of probably would be correct actually to go less than. It's just sort of really a rounding error. Just sort of justify, use one and stick with it. Okay, so the probability of x less than or equal to 72. Okay, so what we have to do here is go back to our correction table. Okay, now essentially what I'm going to do here is I'm going to use this one that I have highlighted. Okay, But actually, you could use the one below as well. But this is the one I'm going to sort of use for this question. Okay, as long as you sort of stay consistent with the whole way through, it doesn't really matter. You just sort of keep it consistent. So what I do here is I change it to 72.5. Okay, when I switch from x, the Poisson variable, to z, the normal variable. Okay, so that's how the 72 becomes 72.5. Okay, so what I'm doing here is essentially calculating a z score, 72.5 minus 84, which is the mean and the variance. Here lambda equals 0.14. So 600 times 0.14, 84. Okay. Square root of 84 is the standard deviation. Okay. So essentially what we get here is probability of z being less than minus 1.255. Okay. And whichever way you work that out, you should get an answer close to 0.105. Okay, so there's a number of different ways you might work it out using statistical tables or so on, or you should be really familiar with the normal distribution at this stage if you're tackling these sort of questions. Probability of z, yeah, there, have it up there. So that is the probability value that we're looking for here, and that really answers our question. So we might as well leave it there.